Good evening, ladies and gentlemen, and welcome to another edition of the Windsor Park Neighborhood Association's Climate Conversation. My name is Martin Lukey, and I'm the chair of the Windsor Park Climate Crisis Committee. And as always, I'm joined by my co-host, Barrett Sundberg. And tonight's episode, we are talking about Gulf Coast sea level rise. Barrett, would you please introduce our first guest?
Dr. Rhiannon Bezore has a PhD in coastal geography from the University of Melbourne in Australia. She joined the Hart Research Institute at Texas A&M Coastal Marine and Geospatial Lab in April of 2020. As a research specialist, her research interests include using GIS and remote sensing techniques combined with field work to monitor and model coastal geomorphology over short and long-term changes in the environment, modeling sea level rise impacts on coastal landscapes, and helping communities improve their resiliency in the face of coastal hazards. So welcome, Dr. Rhiannon Bezore.
Thank you so much for having me here. I will go ahead and start sharing my screen, if that's okay.
Well, hang on a second, Rhiannon. We're going to introduce our other panelists, and then we'll start the sharing.
No problem. Sorry about that.
Cheers, no problem. Our other panelist is Bruce Melton. He's a professional engineer, environmental researcher, filmmaker, climate science education specialist, author, and director of the Climate Change Now initiative, founded in 2005. He has written over 500 reviews of academic climate science, lectures regularly, and has recently been involved in groundbreaking climate policy development, where he was awarded a Special Achievement Award by the Sierra Club for helping in the establishment of new climate policy and a safer limit to warming of less than 1.0 degrees Celsius above normal. Bruce, welcome to the show, and thanks for joining us. So Bruce, go ahead. Everyone turn on your cameras, turn on your microphones, and we're going to start the conversation now. Both of you have been doing a lot of research on sea level rise, which is something that we hear a lot about, and in fact have heard about this since at least 1999. And so we've now had a good 2 decades of research done on it. And it's time to find out where we stand on that. And as I understand it, Dr. Bezore, you have a presentation that's based upon research done at the Hart Research Institute there in Corpus Christi. If you would please just go ahead and show us what you've got.
Absolutely. So thank you for that. Today I'm going to be talking about climate change and specifically sea level rise and how it affects the coastal zone in general, but specifically in Texas, because we have a fairly unique and special coastline, as I'm sure you all know. So again, I am a researcher at Hart Research Institute at Texas A&M in Corpus Christi. My lab specifically focuses on using geographic information systems to map and to model and to analyze different coastal changes. And one of the biggest things that we look at is sea level rise and how that affects and is going to continue affecting our coastlines. All right. Okay, so I'm going to start off with kind of just a basic background information session here on climate change, and then leading up to sea level rise. So on the far left here, you can see the annual greenhouse gas index. And can you guys see my mouse moving here?
Yes, we can see it.
Okay, perfect. Use that as a pointer then. So greenhouse gases basically act as a trapping mechanism or a blanket effect that as the sun radiates heat down to Earth, most of that heat is then bouncing off the Earth and radiating back out to space. But the way that the greenhouse gases work is that they trap a lot of that heat in the atmosphere and hold it in, creating a warmer atmosphere over time. So you can see on this graph here, we have carbon dioxide in the light blue, methane in the dark blue, nitrous oxide in the light green, and then what are we refer to as chlorofluorocarbons here in the dark green, and then other halogenated gases in the yellow. So you can see that we're mostly concerned with carbon dioxide when we're talking about greenhouse gases. It's not the only one by any means, but that is what we'll be focusing on for the main driver of climate change in this talk. So when we look at past carbon dioxide levels in the atmosphere, before 1958, we are looking at ice core data. So the components of the atmosphere are trapped in ice over time. And so we can go back and cut those ice cores open and actually analyze what the atmosphere was like during that time period. And we have these ice cores dating back eons and eons ago. But this is showing from 1950, or sorry, from about 1600 to present. Okay, so you can see it's holding fairly steady. And then when we get to about 1950, you can see this really sharp rise here. And the rise really starts post-industrial revolution. So once we started producing more and more goods over time, we were releasing a lot more carbon dioxide into the atmosphere. And then post-World War II in the 1950s and 60s, you can really see that production starting to ramp up as we have these huge factories producing cars and goods, and we're seeing more and more of these goods shipped elsewhere, both nationally and internationally, creating a lot more CO2 over time. And so you can see that, again, this was from up until the 1958, it was all from ice core data. After that, we started collecting data via satellite measurements at Mauna Loa in Hawaii. And it's measured there because it is really clear. It's a very high peak. You're able to collect a very nice, clean sample of the atmospheric composition. So we rely on this Mauna Loa data from 1958 onwards. And you can see that really sharp rise here moving forward. And in this bottom graph here, this is just zoomed in from that Mauna Loa data. So from about 1958 to present. And we refer to this as a hockey stick curve just based off of its shape. And you can see that it is increasing greatly over time, pretty steadily and exponentially. And the reason why there's a black line here and a red line is that carbon dioxide fluctuates over seasons. So during summer and spring, plants are photosynthesizing, they're taking in a lot more CO2. And then over fall and winter, as those plants and trees start to die off, they release a lot of CO2 back into the atmosphere. So you'll see that kind of oscillating trend there. So the black line going up is just showing that seasonally corrected curve. So it's averaging out the winter to summer trends there. So either way, you can see that CO2 is increasing very, very quickly. So as I said, greenhouse gases and specifically CO2 act as a warming blanket effect basically for the atmosphere. So some of the things that we see with these greenhouse gas effects are higher humidity in the atmosphere, higher air temperatures, higher sea surface temperatures. And for the air temperature, it's not only just in the atmosphere, but also at the land level too. So land surface and sea surface temperatures are increasing. Because of that, we're seeing a lot of sea ice melting. So the sea ice is decreasing over time. And we're seeing a lowering of the land, snow, and glacial coverage as well. And so when we're talking about sea level rise, the type of ice melting that we're more concerned with is the melting of the land ice and the glacial coverage. Because if you have ice that's already in the ocean and as it melts, that's not actually contributing to the rising of the seas, but the ice that's melting and running into the oceans from land, that's going to help rise the sea level. So this graphic is just showing basically what we just went through, the different concerns that we have with these warming trends and what we can expect to see as temperatures continue to increase. This graph down here shows the global land and ocean temperature anomalies between January and November. So it's using about 1950 as a zero marker. So anything that was higher than 1950 levels is going to be in the red, and anything lower than that will be in the blue. So you can see leading up to 1950 that temperatures were fairly cool from January to November. You see some times where that was not the case. There were some warming trends going on there. And that could be due to things that were going on in the economy. It could be due to El Nino versus La Nina years. There are things that can cause some fluctuation. But from about 1950, 1960 onwards, you can see this very sharp warming trend again. Okay, so it's kind of matching that CO2 line, right? That hockey stick curve. And then over on the right, we have the land and ocean temperature percentiles. So basically we're looking at where the warmer areas are versus cooler in blue and the warmer in red. So you can see overall there is a much more pronounced warming trend for both land and sea versus the blue areas where there is some colding trends happening. And so that's one of the reasons why we as scientists prefer to say climate change now versus global warming, because it isn't a global warming event. Some areas are cooling, some areas are getting warmer. There's a lot of fluctuation and variation in where these patterns are being seen. So it's a change versus one specific trend. And you can stop me at any time if you have questions or if I'm going too fast too. Okay, so when we're talking about climate change and the coastal environment, there are a number of different things that we're going to be concerned about, okay? One is air quality. So if you've heard of the ozone layer, right? The ozone layer is a good thing. It protects us from harmful radiation from the sun. But there's something called bad ozone or ground level ozone. And this is produced by pollution combining with and reacting with sunlight to create harmful ozone that is close to the ground level. And so in Houston and Galveston areas, they already are classified as an EPA severe non-attainment area due to the levels of bad ozone that are in the atmosphere near that area. And that means that the air quality there doesn't comply with the national ambient air quality standards for a given amount of time or certain number of period of days per year. So that is expected to increase over time as we're seeing more pollution and warmer days. There's also an increased risk of fires. So last year, you probably remember the fires in California and in Oregon and in Colorado and most of the Western states. And so even if you don't have a fire specifically in your state or in your area, that can still affect the air quality. If you remember during those fires, a lot of that smoke was going all the way across all of the states over to the East Coast. A lot of it was heading down towards our way. And even at the coast down here, we were seeing bright red fiery sunsets from that smoke in the air. So that can again increase fire risk over time with just warmer, drier weather. Precipitation.
Like we're not only making our own pollution with the ozone, we're getting other people's fires, both partly from the climate change.
Exactly. So it's not even just what's in your own backyard. You have to worry about states, hundreds and thousands of miles away now too. And everything is all interconnected. With precipitation, it's much like with the warming trends. Some areas are going to be seeing increased precipitation, which can cause more flooding, more intense flooding, and more frequent flooding. And then a lot of places will also see increased drought. So we're already seeing in the West Coast a lot of drought, year-long droughts. I'm from California, and we had a drought for about 4.5 years. It looked a lot like these pictures here, this center picture there. A lot of agricultural land suffered, farms were shut down, crops and farm animals died over that course of time. And then on the other hand, with the flooding, you can also see crop loss during that as well. In Texas, down here in the bottom picture, you can see expected drought trends for this year. So the dark red means a higher increased drought risk, and then the lighter colors are a little bit less high risk. But you can see along the coast, there are still some areas of higher risk. So this isn't just an inland issue. This is a kind of statewide and nationwide issue that can happen. All right. Something else that we're going to be seeing more of are these extreme weather events. So again, we're going to be seeing a change in both the geographic pattern of them and in their intensity and frequency. So areas that might not have had a lot of hurricane landfalls before might start seeing more hurricanes. So specifically like on the East Coast, somewhere like Maryland that is typically just kind of out of the hurricane zone, they're kind of on the outskirts, they might be seeing more hurricanes. So we'll see a shift some places. In some places, we might be seeing just an increased risk of higher category hurricanes because there's going to be warmer air and wetter air from the higher humidity. You'll see an increased frequency of the hurricanes as well. So not only are they going to be higher category, but you might have more of them. And we're already seeing that kind of trend over the past couple of years as well. Last year was the most active hurricane season. We had, what, 31 storms, named storms. We ran out of the alphabet and had to start again with Greek letters. This year is supposed to be fairly active as well, not quite as bad as last year, but still very active. You can see here in the top graphic, so 2021 hurricane season for the Atlantic, blue 60% above normal. This is a probability, 30% normal, and then only 10% below normal season. So we're looking at a fairly active season. They're predicting this range here in the red for the landfall hotspots. So that doesn't mean that the rest of Texas is out of the question for a landfall. This is just where they're predicting. We saw Louisiana last year get hit by a lot of storms as well. So it looks like they're still kind of in that danger zone there. Again, increased temperatures, we'll see more drought conditions as well, which can lead to more wildfires too. Which you can see here in Texas, the southwestern portion of the state is definitely in the most extreme fire danger, but along the coast here, especially in the coastal bend, leading up to the coastal bend, we're still in a fairly high danger zone as well too. Okay. So hurricanes, as I'm sure you all know, don't just affect the coastal zone, but we are that first kind of line of defense that gets hit the hardest in a lot of cases, unless the storm stalls out inland. So some of the impacts that we're looking at would be property damages to life, which is, you can't put a number on that apart from, you know, lives lost, but it's hard to put a financial number on that. Hurricane Harvey cost $125 billion in damages to properties, and mostly that was due to storm surge and high winds. So not only do you have to worry about the flooding, but also the really high winds. Sometimes there's tornadoes associated with these hurricanes. You can be looking at complete changes, partial to complete changes of the beach morphology. So the shape, the size, the different features of the beach and the ecosystems that are on those beaches. This is from Hurricane Ike in 2008, I believe. So you can see in the top picture, it's all vegetated. There are homes, and this is fairly built up beach here. We have some, looks like some armament here, so coastal protection structures. And then post-Hurricane Ike, you can see the vegetation is lost. And vegetation is really important for acting as a protection system for beaches and dunes. It helps kind of hold all the sand in place. So if something doesn't have a lot of vegetation, then that means that that sand is fairly loose to be moved and shifted around. You can see here that all of those houses appear to be gone on that this barrier island system here. and there looks to be some new inlet features, some new estuaries forming here. So it can really rework a whole beach system. And it takes years to hundreds of years to thousands of years for a beach system to reform or to recover in some cases, depending on the sand supply and other factors.
It looks like the skin came off.
Right, just peeled it right back. On the right picture here, during, sorry. So this was after Hurricane Ike as well in Galveston. And they lost 100 feet of sandy beach during that storm. Normally that amount of erosion would take 65 years to cover that much erosion. So just in, you know, a week or less, all of that sand was washed away. So one of the more long-term effects that we're looking at for climate change on the coastal system is sea level rise. Now, there are a few different things that cause sea level to rise when we're talking about climate change. One is that, as we talked about, the sea surface temperature is increasing, right? And the air is increasing in temperature as well. So as water heats up, it expands. So imagine if you have a bathtub and you're filling it up. The bathtub itself, that basin isn't changing dimension, right? It's not getting any bigger or wider or deeper. But as you fill it up, that water is rising and rising. Well, the ocean basin is the same thing. So as the water is expanding and heating up and expanding more, it has nowhere to go but up and out. Okay, so that's why at the coast, it's going to spill over basically. So another thing that increases sea level rise are changes in the surface and deep ocean circulation. So if you have deep water or surface currents, sometimes those change during hurricanes. So more water will be pushed up against the side of the coast. So that's why during hurricanes, you have higher tides sometimes, and they're pushing further and further inland. So we refer to that as storm surge as well. It's just a buildup of water and it has nowhere to go again but inland. Another reason why sea levels rise again is this exchange of water from ice. So as ice melts on land and it enters the water, it's basically filling that bath. Another thing that is a definitely important factor in sea level rise in Texas as well as other places is the extraction of groundwater. And here in Texas, petrochemical oil as well. So as you're pumping things out of the ground, that ground is getting compacted and compacted until it is lowering down, so that any sea level that is rising is going to be effectively higher than it would be if that surface wasn't compacted. And so that can happen from the extraction of water or oil. That compaction can also happen in river delta regions. It can also happen from tectonic displacements. So there are other things that can cause land subsidence as well, but that extraction of oil and water is definitely a big one in Texas.
Dr. Bezore, any idea how far that is? I mean, are we talking about a few feet a decade, or is this measured in inches at this point?
So it is measured in inches. It depends on how far into the future we're looking. We'll see some different rates historically and in the future in the next couple slides too. But if you're talking 100 years from now, that's going to be on the order of possibly feet. If you're talking 30 years for planning purposes, you might be talking a few inches. So it really depends on the time scale that you're looking at. So right now, globally, over the past 100 years, we've seen 0.07 inches per year as the global rate of sea level rise. So basically, over the past 100 years, we've seen 7 inches of sea level rise. And when we talk about sea level, we're talking about the average height of the ocean between low and high tides. So they're measuring that out and then averaging globally. The models for sea level rise show that we should be expecting about another 7 inches over the next 100 years as well. So that's a conservative kind of best case scenario. If we don't control our greenhouse emissions and kind of get a handle on that, the worst case scenario, we're looking up to about 23 inches over the next 100 years. Okay, so it doesn't sound like a lot, but when we're talking about low-lying, barrier island kind of beach systems, that's a lot. If you're talking about somewhere with really high cliffs, like on the West Coast, that might not be such a big deal. So it really depends on where you're looking at. These are globally average sea level changes from 1880 to present. So again, in the blue, that's when we started measuring with satellites. Before that, we were using tide gauges. So on buoys out in the water, measuring that falling and rising of the tides and averaging it out. Zooming in to the satellite data, you can see from about 1993 to present, excuse me, you can see that increasing trend really pick up from about 93 onwards. But it's been a pretty steady rise from about 1880. And it also follows that CO2 and temperature increase curve pretty well. When you put them all together, they all have the same size, same shape, same trend.
So we have a question from one person who's listening.
Yeah.
In fact, it's our volunteer Selwyn who's doing a very good job of managing the screens and kind of running the presentation of the call behind the scenes. And he asked if it's 23 inches on average everywhere, is there much variation between different places?
That is a great question, and actually leads us perfectly into the next slide too. So when we're talking about global averages, that doesn't always reflect what's happening on a smaller scale, a more regional scale, right? So that's the difference between global sea level rise and relative, or sometimes referred to as regional sea level rise. So regionally in Texas, and especially in the upper Texas coast, we're seeing rates that are a lot higher than the global average. Now, before moving to Texas, I was living in Virginia for a couple of years in Norfolk, and they have crazy high sea level rise. So it's all relative. When I was in California, the sea level rise rates were not quite as high. And again, that's because we have cliffs, we have tectonic activity creating uplift. In Texas, again, we're looking at that land subsidence from the groundwater extraction and oil extraction, lowering that surface level of the land and making the effects of sea level rise a lot higher. So since 1908, Galveston has seen about 2 feet of sea level rise, and the rate of rise there has been 0.24 inches per year. Remember back to the global rate of 0.7 inches per year. It's a pretty big difference between the global and the local or relative sea level rise. So any area that has less land subsidence or more tectonic uplift is going to see lower rates of sea level rise. There's a part of the coast in Alaska that has such high tectonic uplift rates that their sea level is actually lowering or staying fairly level. So it's not that big of a deal for them right now, but other places like us, it is definitely a more pressing issue. And you can see in Texas, it changes from place to place too. So the yellow is 3 to 6 millimeters per year, or feet per century is 1 to 2. And so that's kind of where I am around here in the coastal bend, versus red up here in the Galveston area. And then you can see in Louisiana as well. Some places along here, a little bit lower. So from place to place, it definitely changes. And you can, it can be from county to county. It all just depends on the geology and the other factors that are going on at that specific location. So when we talk about the coastline of Texas, we're talking about a few different features, and we'll go through how sea level rise is going to affect each of these two. So the first one is the Gulf of Mexico. Okay, so this is our ocean here. Gulf, obviously, so it is more enclosed, but that is the exit to the open ocean here. Moving inland, we have barrier islands. So some of the things that we'll see along the barrier islands are beaches and sand dunes. A lot of buildings that are built on these barrier islands are elevated or might be kind of set back a little bit, not in all cases, but there are certain features that we'll talk about that can be used as kind of adaptations for living on these barrier islands. Behind the barrier islands, you'll see bays and estuaries forming. So these will be brackish, meaning that they are a mix of fresh water coming from inland and salt water coming from the oceans. And a lot of very specific conditions in these estuaries and bays allow a lot of marine life or estuarine life to live there. So plants and animals that are only able to live in very specific conditions. Moving inland, you might have some man-made barriers such as coastal protection structures, so things like seawalls, revetment, so those large riprap boulders that you see kind of stacked upwards in a kind of a triangle shape, different groins or jetties. And then the inland area, by inland, I mean kind of the coastal zone where most people live along the coast. So starting at the seaward edge and moving inland, we'll start with the barrier islands and sand spits. So you see here, the Texas Gulf of Mexico shoreline is 373 miles long. There are 7 barrier islands along the coast of Texas, though, that comprise 234 miles of coastline. So most of the Texas coastline is comprised of these barrier islands and sand spits. The average age of the sand spits is about 4,000 years old, and they all formed as waves move sand delivered to the Gulf by coastal creeks and rivers and deposited that sand in these elongated shapes. And they act to provide a lot of protection from waves and from storm surges for the estuaries that are landward and for the mainland of Texas. And there are a couple of ways that these can react to sea level rise. One is that if there's a slow sea level rise happening, they can actually deposit more sand and create more sand spits and barrier islands over time. So you'll see an increase of these features. But if sea level rise is happening really quickly, it will outpace the deposition of the sand and it will eventually drown those features or move them inland towards land. So that eventually that sand spit will become either a beach or part of the sand dunes or just be washed away. Anytime you have a lot of storm activity, which we're expecting to see more of, you're going to see a lot of erosion of these sand spits and their beaches and the dune systems. The seaward side of the barrier islands is about 6 to 13 feet above sea level on average, and the bay side is about less than 4 feet. So these are really susceptible to any level of sea level rise. Okay, on the back side, the landward side of the barrier islands, we have wetlands and estuaries. These are marshy environments. And whereas the 234 miles of coastline were the barrier islands, because these wetlands are really winding and bending and have, you know, funky shapes to them, they actually make up about 5,840 miles of coastline. So it's a pretty extensive system. And they are bordered by tidal flats and salt marshes. Again, there are, they provide a huge amount of habitat for birds, fish, ducks, shrimp, crabs, marsh, and wetland plants, pretty much just a host of different life that lives only in these types of environments. And they are very specifically adapted to the conditions that are in these areas. So the amount of salt, the salinity, the temperature, the amount of sunlight that they get, And if there's any change in any of those conditions, they have a really hard time and will either have to migrate elsewhere or will die off.
So if somebody's saying, oh, well, it's just the water's gonna be a foot higher, but everything moves, there's no change, that's not really what happens there.
Exactly. There's some cases, which we'll see in the next slide too, wetlands and estuaries can migrate inland, but depending on what is inland, they're not always able to do so. And because they provide so much protection for the shoreline, the closer they get to the shoreline, the less protection that they're able to provide. And they also filter out a lot of pollutants too. And so they act as a kind of an ecosystem service in a lot of ways. So they're good for the environment, they're good for humans. You can use them for recreation. People go bird watching, boating, fishing. So without that, we're also talking about a lot of loss of tourism too in those areas. So these are all fairly close to sea level. So they're very vulnerable, again, to sea level rise. And the three main concerns that we have for these features are one, erosion. So any kind of wave attack on the wetlands and the shorelines is going to increase as the water continues to rise. And it'll push them further inland, or it'll erode that sand and those tidal flats away, which will allow for less protection. The second is saltwater intrusion. So again, those wetland species have a very specific set of conditions that they can live in. If that salinity from more salt water coming in increases, then they're less able to survive in those conditions. And then the third is inundation. So as Barrett said, sometimes these features can move inland, they can migrate landward, but if sea level is rising too quickly, they're not able to keep up and they will drown, as we call it. They will be inundated by salt water and they'll just become open ocean, basically. They're no longer specifically wetlands. If there are structures on land like seawalls or other types of protection structures, we have what we call coastal squeeze. So that means that there's nowhere for those features to migrate inland. There's a hard surface there, and so they get squeezed closer and closer until it's just ocean at that point.
This is, I thought.
Sorry?
I said, this is worse than I thought.
It's not all doom and gloom, I promise.
Our attempts to control it are not going to work. They're going to make it worse for the protective species.
There's a lot of restoration projects, though, that are happening nationally, but also in Texas. So they're really focused on maintaining the environments that are there and expanding them as well. And there's a lot of protection structures. They put things in like living shorelines. So these are oyster reefs, or they're we refer to them as soft structures. So instead of a seawall, it's something that can help develop more wetland area. And there's wetland planting, things like that. This example down here in the bottom, oops. This is a Galveston Island Park marsh restoration and protection in Karankawa Cove. And so you can see that these are all plants that have been planted, expanding this marshy area. They put in some soft structures here so that the structures can expand as needed versus just having a hardened shoreline there. And then they have built a breakwater out here as well. So this marshy land here can expand outwards towards the sea. And so they're kind of building more wetlands. And a lot of these projects are happening nationally and internationally. It's kind of the way to go right now. And a lot of governments are actually saying that this is their preferred method of dealing with coastal armament and with coastal flooding issues. And so that's really good. It's kind of a positive step forward.
I'm curious how much something like that costs to do per, I don't know, mile.
So they're actually Sometimes the startup cost can be, the initial cost can be a little bit higher, but your return is actually greater than it is with hardened structures because it's increasing in value over time versus when you put in a seawall or a groin or a jetty, the second you put it in, it starts depreciating in value. And
So what's an example of one of these soft structures? I'm just trying to imagine.
So they have these soft kind of, they almost look like inner tube structures that they can fill with different debris and stuff like that. And they are eco-friendly. They put them in. So instead of putting rocks or concrete or concrete slab, something like that, it holds the wetland line in place, but plants can also grow out of it, on it. They also have the oyster reefs that they put in, so you're increasing the biodiversity in the area too. They have oyster balls as well, so they're like kind of these almost like soccer ball looking things that the oysters can grow on and around. And so it's ways of hardening that shoreline, but without putting in structures that are going to decrease the ability of wetlands to grow.
Dr. Bezore, I want to break in for a moment here. We are now 40 minutes into the program. We haven't had a word from our other panelist, Bruce Melton, and I'm realizing that we maybe should switch over and start kind of having a conversation here. This is all absolutely fascinating. If you can do maybe another page or two, then let's get to some of Bruce's work.
Absolutely. So sorry about that. Let me get through. Yeah, this would be the last slide here. So we'll end on how this is impacting humans as well. So about 6.5 million people live in the Texas coastal zone. We have even more people coming for tourism each year. And our Texas shorelines are projected to retreat up to 4 feet per year. So this is an issue that's happening right now. It's going to happen more in the future. So we really need to start looking at ways to kind of go about fixing the issue or thinking about solutions of how to react to the issue. And it's important to note that what happens here can impact the national economy too, in terms of our oil export, our tourism. It's not an isolated issue. So what are our options? There are 3 main ones. The first is to adapt. We can do things like the wetland and marsh restoration. We can build more coastal protection structures, so those hard structures. And then we can also encourage more resilient planning too. So putting houses up on stilts, maybe building flood walls around houses or structures. Our second one is retreat. So that is usually kind of a dirty word in the coastal planning arena, but really it just means that you can enact setback laws for new development, so you can't build right at the coastal zone. If homes are frequently flooded, maybe having a buyback program from the government. And then the third option, and I don't put this to be glib, but is to do nothing. That is an option. A lot of places aren't choosing to do anything. And so they kind of just deal with the flooding as it happens. There's flooding, you repair it, more flooding, you repair it. And so we really need to kind of pick a plan and move forward with it. And that's kind of our best bet in terms of how to deal with sea level rise and climate change in the coastal zone. And so I don't want to leave you with all doom and gloom. I think that, there are solutions for this and there are ways forward. We just kind of, again, have to pick a plan and move forward.
Well, that's really eye-opening. If you wouldn't mind unsharing your screen so we could talk about this a bit. Bruce, you have spent how many years looking at the Gulf Coast with the work that you've been doing?
Officially, since 2005 is when I started the Climate Change Now initiative. I've been a beach rat my whole life. I grew up down there and got some great pictures to show you. I can run through them real quick.
Yeah, please do share that with us and explain to us about your photography. Basically, you've just started taking pictures back then and you just continue on now?
You got it. I've been a high resolution photographer for 40 years. and got a lot of good stuff. So let me go through here. This is South Padre Island of, I can't see, I can't remember
It says
exactly.
2014.
2014. And that's one of the last remnant natural beaches. Then this was some time ago. The beach got washed away sometimes between 2000 and 2013. Most of the beach on the lower Texas coast got washed away. No subsidence to speak of, except in Rockport, there's a new area of subsidence. The subsidence doesn't really hit until you get to the upper Texas coast. This is my outfit since 2005. I'm a professional engineer, literally the oldest independent climate science education organization in the world, or at least in English-speaking countries. We do things a little bit different. Global warming psychology says that we've failed using traditional analytical science learning with climate change for many, many reasons, and the money is just one of them. So what they say is we need to do outreach, to learning with right brain strategies, and
That's why we have this program, Bruce.
that is exactly it. It's you show people and you tell people. You don't just make them read it. One of our big deals is filmmaking, and our latest film project, the last 6 years, not including doing nothing during COVID. I had one trip, South Padre, over 50,000 miles across North America. Our first film was nominated for award at Austin Indie Film Festival. It's called Inglorious Events. You can find it on the website at Climate Discovery. This is the band. We played together over 700 times. We just got back together. We missed 63 weeks. We've played together over 700 times since 2002. And we play for my documentaries, and we play for the Angels, and we play a couple of charity gigs a year, and that's it. But it's just amazing. We've played together 3 times now since we've gotten back from COVID, and I just can't tell you. Melton Engineering, that is what funds everything. I'm having my biggest philanthropic year. I've raised about $6,000 so far this year. It's the biggest ever since 2005. So I have to fund things from my engineering services. I do residential commercial flood work, which is real important with all the rain bombs these days. So you guys send me some business. And I had to include the title slide from another presentation I did down in South Padre 4 or 5 years ago, just because I liked it so much. This is what it's all about. This is non-storm conditions. This is king tide. This is a piece of beach art. There's a really cool artist in South Padre that does beach art anonymously, way up the wild beach. You can see him back off in the distance, and it's cool. 1978, I started going to the beach. My parents started taking me. I lived in Houston area long before I was able to grow my hair long and play Frisbee and lots of other things. But look how big the beach is. This is Surfside. Surfside is one of the worst subsidence areas on the Texas coast and in the nation and in the world. But look how big this beach is. This is before oil and water extraction really got going down there. And it's literally 100 yards wide and lots of fun down there. This is Surfside today. This is an Army Corps of Engineers remediation project. They tried to build some dunes. Never build dunes out of red clay. It just nukes the beach. And one of the big deals with remediation is that it's going to have a really hard time working because sea level rise is so high. My data on that is a little bit different than the consensus, and I'll get to that. But this is Army Corps of Engineers. This isn't working. This was about 18 months after it was installed. 1984 is the first time I spent any real time on Padre Island National Seashore. The year I graduated from college, me and a buddy of mine went down there, and we did not want to come back. We stayed for a week, only went out to get beer and ice, and came back to Austin. And then we went back again for another week. Me and my wife, same place, 7 miles past the 4-wheel drive only sign, big beach, big fish. I'm standing on the high tide line. The tide normally does not get any higher than this back in the day. She's why I'm here. She has supported me so much. Thank you. I mean, just huge beach. And, you know, this was way before I started doing this. I was just down there fishing and having a good time. Big beach, 7 miles past the 4-wheel drive sign. This is where a little shell starts, if any of you guys are familiar with the landforms down on Padre on National Seashore. 2003, still a huge beach. And you notice here, we got all sorts of sargassum weed. This is seaweed. We had a heck of a time for about 20 years with seaweed. It's gone away for some reason, and I'm not real well versed on that, but it's gone now. 2003, I got a 4-wheel drive mean beast so that I could go further and further. This is 35 miles past 4-wheel drive sign. Back in the day, it was murder. It took all day to go 35 miles. This is almost at the Mansfield Pass Jetty, 2003, with the 1990 Suburban solid axle beast. Solid axle beast again in 2005. Where is this? About 50, mile 50, way down the beach. I mean, there's nobody down there but a few fishermen. Another piece of art from that cool artist, South Padre. So consensus sea level rise. Rhiannon talked about this. 2 feet by 2100 does not include dynamical ice sheet collapse. Dynamical ice sheet collapse, that's a real thing. That's a real word. It's what happens now. It's happening now. It is active. More than half of climate tipping points. We've heard of these tipping points that are supposed to happen, dystopian things, way in the future, after 2100. Climate science is very understated. More than half of tipping points are now active. Many of them are irreversible. We don't know when they complete their activations, but when they do, sooner rather than later, in decadal time frames. Some of them may have already completed. They become irreversible. Permafrost collapse. We've got 2.3 gigatons of carbon dioxide being emitted from 1.2 billion acres of collapsing permafrost right now, 70 years ahead of projections. Permafrost, what's collapsed already, we're not getting it back. We can stabilize it, but some things are already beyond the point of no return. Prehistoric sea level rise, 10 to 20 feet per century for centuries on end. It's caused by ice sheet collapse. Climate forcing today is 100 times greater than we've had in prehistoric times before mankind started burning fossil fuels and creating all sorts of havoc with land uses. That should be, no, that's right, 2019. It's Noah Sweet, William Sweet, 2020. 1.5 inches of sea level rise in 2019. Double the previous record. That's from all of the lower 48 tide gauges, 38 millimeters in 1 year. Double the previous record. I'm sorry, I do not know when the previous record was set. I assume probably correctly, it has been very recently. We have seen a significant uptick in the sea level rise trend in just the last 5 to 10 years. The beach started becoming eroded, started going away, literally going away. The increased sea level rise pulls the sand out and storms cannot replenish it. Started happening in 2000. By about 2013, it was generally gone during high tide periods, during king tide periods, but we're having so many of these today. Let's see. This is a recent drone shot, 11 miles beyond the pavement on South Padre. You can see the dune erosion here very clearly. That's the angle of repose. That's the highest angle that sand will stack itself before it collapses. And it is collapsing. You can see there's only one sand dune. There's another sand dune way down here. This is a place called the Narrows. It's a historically high erosion rate at the Narrows on South Padre, but we've seen even, low rates, high rates, everything is increasing radically. And now we're seeing dunes someplace completely eroded away. This is a king tide. This is about 1.85. I did some calibration, 1.85 feet above mean sea level.
Just for those of us who are not familiar, so what does king tide mean?
Oh, king tide, sorry. That is when the sun and moon align just right, called a lunar tide. And it happens in the spring and the fall, mostly in May and mostly in October. But we're having one actually in 9 days to 25th. It's going to peak. There's 4 or 5 of them during the king tide periods, and they cycle about 10 days to 2 weeks, and you get 5 or 6 days where the tide is really high, 20 to 30% higher than a normal high tide. And then you get more normal tides, and then you repeat, and you do that 4 or 5 times, and you have a king tide season.
So how much higher is it in like inches or something?
A foot.
A foot.
And it just depends. It can be 2 or 3 feet higher if you get a good wind. If you get something screwy going on with currents, like South Padre, the predominant current is northward. The North Texas coast, the predominant current is southward. They meet at a really convenient place, the coastal bend of Texas. And that meeting point moves up and down the coast, depending on what time of year it is, on whether or not you got a lot of north winds from northers or big south winds just from normal conditions during wintertime. So anyway, that's enough on
Bruce, I got a question for you. In this photograph that you're showing us, this is a king tide here. So this is the highest that it basically gets. When this goes down, how much beach would be showing if it was not a king tide? Would there be 10 feet of it, or 20
you get about
feet,
100 feet. I've got some
feet?
more. I've got some more pictures of low tide.
And
And
we're running low on time here, so I wanted to show us a couple more, and then we need to have a bit more of a conversation.
High tide at 1.85 feet. High tide, king tides usually run 2.5 to 3 feet. So that wasn't as high as it gets. It gets a lot. It gets where it's unpassable. This is the big dune on Padre Island National Seashore, 25 miles beyond the 4-wheel drive sign. Beautiful place. This is the Devil's Elbow, basically the bend of the coastal bend of Texas. This is what's going on 2003. This is a series of that shows us the loss of the beach. Here we go in 2017. This is actually low tide during king tide. So we've got a very significant beach erosion going on. This is not high tide, but it's not low tide either. It's middle tide. South Padre Island is one of my filming trips down there, 2017, non-storm conditions. Here's some dune bergs. See this right here? This is a block slump. And see that angle of repose right there? The surf washes away the toe of the dune, and then you get this big block slumping down into the surf. And then it just keeps slumping and keeps washing away. This is an area where the dunes have been completely washed away. You can see that angle of repose right here. The black sand is magnetite. It's left behind. When the sand is pulled out into the Gulf, the heavier magnetite iron sand is left behind. Google Earth, here's another series on South Padre, 2017, 2011, 2009, 2008, 2002, 95, 250 feet. This is the dune line. This is what we were looking at earlier was the beach, but this is the dune line. A little bit different thing, erosion thing. Just wanted to show this magnetite again. This is a pretty strange thing. Never seen black sand before 5-6 years ago on Texas coastal beaches. What we've got going on is we have crossed the beach and wetland disintegration threshold, 7 millimeters per year. this report by the Army Corps, the Global Change Research Program, was prepared on in the Northeast. Is Hatteras, the Delmarva. These are all barrier islands, exactly like we've got on Padre. This phenomenon of a 7 millimeter per year sea level rise is endemic, or it's the same with barrier islands everywhere. And what we've got is scenario 3 going on right here: greater than 7 millimeters sea level rise per year, widespread, almost total beach erosion, wetlands conversion to open water, unrecoverable barrier island disintegration. That's where we are right now in a lot of the barrier islands on the Gulf and East coasts. It's not the average that gets us. It's the extremes. It's these high tides. One thing I didn't mention back when I was at the number of king tides, 53 times between June 2018 and May 2019, we had a tide that was eroding into the dunes on Padre Island. That in normal is nearly zero. These are non-storm conditions. It's the recent trend that matters. 1.5 inches of sea level rise in 2019, double the previous record. 38 millimeters per year is 10 times the global long-term average. What's going on is non-stationarity of data. It's really difficult to robustly acknowledge a recently changing trend with statistics and with academics. But what we're doing with my initiatives is we're showing people, and it's what matters is the extremes. And this is Ike. This is at the Big Dune on South Padre. This is as far as I could get down. This is as far as they had cleaned the beach. It was just totally impassable. All this stuff came from Galveston Island, and it washed up on South Padre and in the National Seashore. This
Chris,
is
your pictures are really powerful. I know we're hitting about 8 o'clock or an hour or so.
This is the
Some
last
of our
shot.
viewers
I think
may
this is
need
the
to
last
know
shot.
where to see your pictures.
See them I didn't put that in here, climatechangephoto.org. But the most important part is it's devastatingly beautiful. The most important part is climate discovery. Climate Change Photo is, it's a new website. It's got my high resolution work on. I've only got two galleries up. The beach gallery is one of them. Permafrost is the other.
So Bruce, if you wouldn't mind unsharing your screen for us, climatediscovery.org is where we find you.
That's it.
Okay, brilliant. Rhiannon, I was wondering if you have any reaction to what you've just seen from Bruce.
I completely agree that I think showing images is one of the best ways to get people on board. Depending on where you live, people are more or less resistant to hearing about these kinds of things. And so actually showing images that aren't just of storms, but of our everyday conditions that are what we are going to be seeing more and more of in the future, that's a really good way to help people visualize what is coming their way, because a lot of people are either in denial or kind of on the fence about these types of things, but showing both the science and the visualization of what to expect can really kind of push people towards being more active.
I recently saw a New York Times article on the city of Miami planning on building a 20-foot seawall around the city, 6 miles long. It'll cost, at this point, the Army Corps of Engineers says it's going to cost $6 billion, $1 billion a mile. And that is a really high seawall, 20 feet and of course, Florida is very porous. So the ocean is just going to sneak up from behind and fill up behind the seawall. So it seems like the only thing that's going to do is, I guess, stop a storm surge.
It's not likely to be approved. And that is the deal, that the only thing it's going to do is stop the surge from nuking the bottom couple of floors of the big buildings and whatever small buildings are around. because you're exactly right. The karst geology in almost the entire state of Florida will not allow the seawall to do anything.
Rhiannon, you said seeing these pictures and visualizing, you know, the kind of data you've been talking about might encourage people to be more active. What should people be doing?
I think the first thing is, like everybody here is doing, is to be informed, to want to know more about what's going on, so that when it comes time to vote, you're voting in, you know, a way that is taking climate change and sea level rise into consideration. So that if you're sitting on the, you know, a city planning board, or if you know people in the government, you can kind of share that knowledge with them as well. If it comes time to vote on a bond and it's for something like a seawall versus more a green infrastructure, or, you know, a wetland restoration project or something like that, you know what they're talking about in either way, and you can make an informed decision. And I think having that knowledge is definitely helpful. It's the first step. I think there are so many new and innovative and really forward-thinking ways of dealing with climate change and sea level rise in the coastal zone that we don't have to rely on things like 20-foot high seawalls. We can rely on other types of projects and kind of help push those through instead.
I've got a different take. I made these comments on the Ike Dike, the coastal spine project that is being pushed in Houston right now. Unfortunately, they have changed from a structural barrier to a sand dune barrier, but it still doesn't, you know, same thing's going to happen. You can't stop what's going on unless we restore our climate to within the boundaries of its original evolution. See, the ice sheet collapse is happening now. It likely becomes irreversible at some point, probably about mid-century. This is nascent modeling. The modeling has only just very recently become anywhere close to viable with ice sheet processes. And what it's saying is that we've got to cool the oceans back to evolutionary boundaries where the ice sheet was stable, that we knew, you know, in the 20th century. And we don't have to cool the whole ocean, it's just the upper and upper mid levels, which is down to well over 1,000 meters deep, which is no easy thing to do. First, we have to cool the atmosphere. And to do that, we've got to literally remove all of the excess greenhouse gases that we have put up there in the last 250 years. We can do this. The technology is out there to take carbon dioxide out of the atmosphere, to reduce emissions. We've been, you know, working on that for 30 years. Fingers crossed that Biden can get it done. If not, we really need to do things locally. And that's a whole nother presentation, something I've been working on with the city of Austin. But we can take carbon dioxide out of the air to deal with what we can't deal with emissions reductions. Emissions reductions are just in the future. We've got to restore our climate, which means we have to put carbon dioxide levels back to where they were. The technologies were developed in 1907, the recyclable lime potash process in the 1930s, amines, which today are probably the single most important chemical class in industry. We can do it. We can gigascale it. We can do it relatively really cheap, as cheap as what we spend ensuring safe drinking water across the planet every year. We can spend that kind of money. It is you know, tens of trillions of dollars over 10 to 20 years, but it's just tens of trillions of dollars. We have $78 trillion global gross domestic product. So we've got to reverse warming back to where it was, restore old climate, or there is no stopping ice sheet collapse. 10 to 20 feet per century for centuries on end. IPCC says that the the feasible adaptation sea level rise rate is 3 feet per century. You know, we're way over that right now. If you look at the trend from NOAA's recent sea level rise analysis at 1.5 inches in 2019, which, you know, that is a peak, or at least it was the last peak. But, you know, also sea level rise, ice sheet collapse is active now and it's increasing. So, you know, who knows, like California wildfires, who knows how big the next peak is going to be.
And we're seeing in the news that they're using states like Rhode Island as the example of how large these ice sheets are when they break off and turn into basically glaciers floating in the ocean. And so the reality is that this process is moving at, like was pointed out in the beginning, it's exponentially occurring.
Mm-hmm.
And that's the problem that I have with this, with all the science that's been revealed and released over the years, is that there's been this exponential part to it that hasn't been accounted for. And so now we're starting to see, oh yeah, it really is actually increasing much greater than just a little per year. It's more like this year it's this much, and next year it's that much, and so forth. And so it seems like the times that we're giving these things to occur are becoming shorter and shorter. Instead of it happening in a century or two, it's going to happen in 50 years. Or in certain things that were supposed to happen 50 years from now are starting to happen now. And so ergo, we have a climate conversation. At this point, Barrett, do you have any other questions?
We have one person. This is just a small question. Do either of you know what dolas are in South Africa? They're another type of barrier. Just throwing it out there. We'll
Look it up.
come back to that another time, I guess.
Rhiannon, do you know what a dolo is?
I have heard of them, but I have not studied them, and I don't know much about them. Yeah, not enough to speak on them.
Is it one of those big sand jelly rolls?
Oh, they're those.
Oh, it's a
so
groin.
yeah. So they use those in California as well. We have them at our harbor in my
Oh, those
hometown,
things.
actually. Yeah, and so they are just another type of revetment structure. They work the same as riprap, which you can see in this the image to the middle right, too, that kind of bouldering structure. And so the way that they are designed is to dissipate the wave energy. So as waves hit them, rather than having like a flat or a kind of angular surface that might provide something for that wave to run up and then spill over, it's supposed to dissipate it, and so it kind of bounces off of it. And they look like jacks, the toys that used to have, you know.
So it basically shatters the wave and reduces its pressure and its force.
Yeah, exactly. So instead of toppling the structure or hitting it and refracting backwards, which can cause issues as well, it's supposed to, just kind of dissipate the force and spread it out in all directions.
And that's used in what kind of scenarios?
So I've seen them against groins or jetties. So usually have like a solid structure and then they're along the side of them. So where I'm from, we have them at the mouth of our harbor. And so it's to block the harbor entrance so that waves coming from either side are blocked. And then it's also to help trap sand on one side because it is an artificial harbor. And so there's issues of sand movement blocking the mouth of the harbor. So it's to help block the waves and to help trap sand.
Gotcha.
In Texas, the Central Texas pink granite is a lot cheaper than pouring concrete into those crazy shapes, but they are really effective. But you can't walk out on them to fish.
No.
You also can't start. They might stop some of the impacts, but they're not stopping the general trend. You know, if
That's the important part.
batches of ice melt, somewhere on land like Greenland, where I've read it's starting to melt underneath the ice.
Oh, that's the big thing in
It
both
seems-
Greenland and Antarctica. That's what I'm saying about we've got to cool the atmosphere and then cool the ocean, because in Antarctica, air temperature is still well below freezing. It's the warming ocean that has changed the equilibrium and is causing melt from below that is creating instability in the outlet glaciers, making them flow faster, increasing, and pretty soon they get to where they're flowing so fast that the ice sheet just collapses of its own weight, literally. An ice cliff will hold itself up at about 300 feet high, but when it gets any higher than that, there's just not enough strength and it collapses under its own weight. The Antarctica is 2 miles high.
So my question on that line is that when the IPCC says things like, you know, maybe a foot or two of sea level rise in maybe by the end of the century, how confident are they? If we pass some of these tipping points and
Not.
it turns out that, I'm asking Dr. Bezore, scientifically, how confident are scientists that it's that low? What if these tipping points go farther? How much higher could it be? Is science really clear on that? Or are we saying a foot or two is, it's consensus that we're in for that, but it could be more?
So the IPCC uses a whole range of different scenarios. Some are more conservative, some are more, I consider, realistic, but I personally think that IPCC tends to be pretty conservative in their estimates for sea level rise and climate and emissions, greenhouse emissions. So that's kind of the bare minimum of what to expect, I think. That could happen. Again, they use a whole range. A lot of governments, local governments, state governments, tend to use the bottom of those conservative estimates in their planning purposes. And so they're looking short term, maybe, 15, 20, 30 years down the road, and with a very conservative greenhouse emissions and sea level rise rates. So if you want to think more long term and increasing resiliency, it's better to use the high end, or at least the bottom of the high end, and think longer term. Because something might be there for 30 years, but if you're building a building that should be standing for 50 to 100 years plus, that's not going to be a very helpful metric.
So what's the high?
10 to 20 feet per year just think about what happened in prehistory. 10 to 20 feet not per year, per century. 10 to 20 feet per century for centuries on end. We've got lots of evidence. That happened when climate was being forced. We're forcing our climate today 100 times more than the changes in prehistory that caused that 10 to 20 feet of sea level rise per century. So we've got the capacity to, with warming we've got today, to actually create collapse that's even greater than we saw in prehistory. Noah William Sweet, same guy, their sea level rise guru, 2017, he said worst case scenario. We need to be using worst case scenario. Almost everything is understated in IPCC and in all science. IPCC is just an accumulation of the last 6 or 7 years of climate science. And it is all understated for many, many different reasons. I mentioned non-stationarity earlier, changing trends. But the worst case scenario that William Sweet with NOAA uses is 10 feet by 2100. And that's understated because it only includes some ice sheet collapse. IPCC does not include any ice sheet collapse, any. And they're very clear about this. And they do say sea level rise could be more than their 23 inches, but it's and that's the reason. And ice sheet collapse, we just can't model it, but we're getting close. We know you guys have all heard the ice sheet collapse stories on television. It started literally, the first reporting of ice sheet collapse was in 2007. It's actually been going on for quite some time. So it's everything is going to be much, much greater. Asymptotic, exponential things, the pot of water on a stove. Emissions, annual emissions are us turning the heat up on that pot. If we stop annual emissions, we stop turning the heat up. The pot still boils. We've got to turn the heat off. We've got to remove all that heat that we put in the sky. And we can do it.
In the meantime, we're still going to have to deal with the effects that are already in action that will be happening. Even if we were to stop everything right now, we're still going to see warming. We're still going to see that kind of lag effect of what's already been done. And so that's where that kind of adaptation and mitigation comes into play, that we, work with communities and try to get people to be more informed, more, active in knowing what they can do, because it's already it's past the tipping point for a lot of these results.
Real good example happened yesterday. ERCOT issued a conservation alert because we had 11,000 megawatts of forced outages, likely because of damage from the freeze disaster. We got close to having another disaster. Conservation helps, but the deal is we're just getting started with summer. And the 100-degree days, it's really, really an exponential equation. 11 and a half days of over 100 was what was the 1900 to 1990 average. By 2000, it was 28. By 2010, it was 34. 2020, 42. The average, that was I believe that was a 20-year average, but it's increasing. Last year it was 49, 49 days above 100, when the 20th century average was 11 and a half.
In 2011, we had 69 days in a row.
And 90 days.
And 90 in
total.
2012. So yeah, the numbers are starting to be really terrifying.
So what we got to do is adapt accordingly, and adapting for like the conservation alert, not 78 degrees. Put your thermostats on 80, 82 degrees. Set a fan in front of you. You don't have to do it, but between about noon, 2 o'clock and dinner time or dark, because that's when we're at risk. The rest of the time, we got plenty of generation capacity because it's just not 105 degrees banging down on the top of your house. So we've got to change our adaptation strategies. Somebody asked earlier, I've got relatives that want to move to Rockport. I want to move to Rockport, but you got to know what you're getting into. You know those evacuation routes, because the storm surges are growing. Ike was a Cat 2 storm with a Cat 4 storm surge. We're seeing these kind of things everywhere. The size of the storms is getting bigger. The rainfall, 60 inches of rainfall in Houston. The Capital Weather Gang says that was a 1 million year storm. They had 3 bullseyes of 60 inches. The Atlas 14, the National Weather Service new evaluation of rainfall in Texas says the 100-year storm is now the 25-year storm. But non-stationarity in data, they assume the data are stationary. The data are not stationary. They're rapidly increasing. When you do that to a data set, you invalidate the statistics. What it means is that the 100-year storm is now the 25-year storm is very conservative. It's not. The 100-year storm is happening. You see it on the news. The 100-year storm is happening every 5 years, every 10 years, every 2 years. We see every year, we see many 100-year storms on our local news. So we got to restore. We got to do it fast. We got to do emissions reductions too. There's a lot of reasons we got to do that. We know how to do all that stuff. We just got to support our local leaders. We've all got to work not only on our climate science, but on our politics. We can't let the deniers gain control again. It could have, Trump could have killed us. It's just that we're that close. The tipping is active now. It wasn't supposed to be active until 5 degrees C of warming, sometimes 2100 or onward. It's active now at 1 degree C of warming. So
that's 80 years ahead of schedule.
Yes, at least. So many things are like that. Almost everything, almost all the impacts we're seeing now are generations to near a century or more than a century ahead of schedule.
And that's what I was talking about when I was saying this exponential idea. I remember in 1999, there were a lot of predictions being made, of course, because it's the turn of the century. And one of the things they said was the ocean's going to go up a foot by the end of next century. And then as the years have gone by, they have been changing that number from 1 foot to 2 foot to 3 foot to 6 feet. And at this point, they're talking about 12 feet in some scientific articles that I'm seeing. And Miami wants to build a 20-foot wall. So, you know, the idea that this thing at 23 inches seems really low when you start factoring in all the other aspects of the planet. I would think that it's very plausible in 2100 that the ocean's going to be up, you know, 6 or 7 meters.
If we get more than 3 feet of sea level rise, the IPCC widespread consensus, 3 feet of sea level, 3 feet of sea level rise is the feasible adaptation limit. What that means is there's not enough money. When there's not enough money, you create economic stress. If the sea level keeps rising and we can't adapt to it, you know, most of our wealth, more than half our wealth is located along the coast in industry and in pleasure. And it's that kind of stuff, the infrastructure, the roads, the electricity, the water, the sewer. You know, we're having trouble right now all over the country in coastal areas with sewer systems because the sea level is rising fast enough that it's inundating the sewer lines. And we're going to have to raise all our sewer lines. It's electrical generation, our transportation system, everything goes to and from coastal ports. I mean, the vast majority of goods are transferred in and out to coastal ports. Yeah, we can dig them deeper, but what do we do with all those people who have to live around them and operate them? You know, it's sea level rise doesn't stop unless you restore our climate. It's this thing with the boundary conditions of our old climate. That's what defines tipping. Once we exceed the boundary conditions, it's 10th grade science, we create collapse and the ecology must re-evolve. It's real simple. It's going to be
that's
pretty.
A very, very strong closing statement, if you will, Bruce. We have a specific, one last specific question that it's been asked for Rhiannon to address, and I'd like to give her a chance to give her a final closing remark as we come up to 8:30 and our final finish, I guess. Rhiannon, do you want to say a little more to the audience about, someone asked, okay, so I have relatives who are interested in moving to Rockport. What would you advise somebody thinking along those lines individually? And what else would you like to say in closing?
All right, and I put this in the chat too, so if anybody needs it there as well. So Rockport, it was hit pretty hard by Harvey. It's definitely still recovering. I would not say don't move there. You know, it's a great place to live. Anywhere in the coastal bend is a pretty cool place to live. It is definitely something that you have to be aware of. I would definitely look at the home history report for wherever they're moving to, see if it was what the damage was like during the storm, if there's been any past flooding events. If it's a frequently flooded property, then probably don't buy that property. I know that some states don't require flooding, past history of flooding to be disclosed to buyers, but I believe it has to be disclosed in Texas. I know in Virginia it does not. So if there is a house that has been flooded multiple times, nobody has to say anything. So I would check that out, check with the real estate agent, look at the flood zone data. If you are within the flooding zone, then that might be something to consider, not wanting to move there, depending on, you know, their resources. Check evacuation routes where the local shelters are. I think just being really aware of living on the coast and what comes with that is a good idea. Do your due diligence, you know, and just be prepared for what is coming. I think it's a trade-off living on the coast. I've always lived on the coast. I wouldn't live anywhere else. but with that comes certain hazards, you know, sea level rise, hurricanes, what have you. So it's again making an informed decision.
They raised Galveston 16 feet after the 1900 storm. I can help you guys raise your homes if you want. You can raise, did you know you can raise a slab on grade?
And
Just
a lot
lift
of
it right
the
up.
homes
Yeah.
down here are on stilts too. So if you know, are dead set on living right in the coastal zone, and right by the beach, that might be a good option too. So there are options. If you're building a house, you can also try to incorporate more resilient designs. So having, you know, your floorboard elevated, having, you know, floodgates. Sorry. So there are things that you can do too.
Real simple things like don't put your stuff on the floor. You know, I went through flooding in Alvin, and we tried to get everything up off the floor, and with the stuff that we missed that was on the floor got ruined. So one of the really simple things you can do: don't have carpets, don't have wood floors. You use some kind of solid flooring. It's not a deal breaker. But it is going to cost more money, and it is going to give you some heartache, but it's all a trade-off. You know, living on the coast, like I said in the notes, I someday want to move to Rockport, and I really know what I'm getting into. But it's just, you know, there are trade-offs. It's value is what you believe it is.
And for the next 20 or 30 years, we're not looking at some actual, real, dramatic sea level rise. It's the 100 years from now that's more or less where we're seeing the possibility of some dramatic changes. But
it's sooner than that. I mean, if 100 years we're toast, because we're well beyond completion of tipping, and irreversibleness is set in, and economic collapse is widespread. It's the, you know, if these collapse rates are valid, and the rates are probably higher than the worst cases. You know, everything has been so far. There's really no reason why it shouldn't be. We're forcing the atmosphere far more than ever before. So it's not. I mean, I'm thinking in my lifetime, depression, coastal depression, because of frequent nuisance flooding, is going to create home prices that I can afford. I mean, I've just been on the beach too much and seen the beach go away so fast. And now it's into the dunes, and some places the dunes are completely eroded away. It's just it's really happening fast, and it's on that exponential curve.
and what it really leads to is the moving of cities away from the coastlines ultimately.
And again, we get economic collapse, that can't happen. If we don't have an economy, we can't adapt. The only solution really is restoration. I've been working with policy at Sierra Club nationally, and I got a lot of these concepts into our new climate policies, that literally climate restoration and adaptation are tied together at the hip. If we allow further warming, there is no adaptation possible, because tipping completes and we go irreversible. If we start to cool, then we know what the boundaries are. We know what to engineer to. And so we can work with that. And we're below this threshold, just this one threshold, the 3 feet of sea level rise per century threshold would create economic collapse. We've got all sorts of other tipping systems that have thresholds that have economic implications. You know, I need to stop talking.
We could go on and on with this subject, as a matter of fact, and we can't. So to y'all in the audience who've stuck with us this entire time, we really appreciate you hearing all this out. This is an extraordinarily important conversation. All of the ones that we have are always very, very eye-opening to myself, and I'm doing this just like Bruce is for years, trying to get my hands wrapped around, or my arms wrapped around how big this problem really is. And as the more we get into it, the bigger it becomes. So with that said, I want to thank Bruce and Rhiannon for being here for all this time to give us all this information. It really has been great to have you all on board for this, and hopefully we'll have you back again sometime so we can kick the can around and get a little more.
Thank you.
Thank
Barrett,
you for
any-
having us.
You bet. Barrett, any last moment words? Your microphone's turned off. Barrett, your microphone is turned off.
Just thanking both of our panelists and looking forward to working on more actions going forward.
All right. So with that, we will be doing another climate conversation in September, and it's going to be a political conversation. And what Bruce was talking about with the Sierra Club, this is our next goal, is to have a real political conversation, what we can do in the United States Congress. And until then, thank you for joining us, and we'll see you next time. Good night.
Good night, everyone.
Oh, and thank you, Selwyn Pollitt, for running the show for us. I really appreciate your help on that, brother.